let's use the second derivative and the first derivative to give detail to a sketch of the graph x to the fourth minus 2x cubed. So first, we can go ahead and make sense of some points on the original function. Let's look at the zeros. So what x value is going to make my function 0? I don't like that color. So what is x to the fourth minus 2x cubed equals 0 going to give us? You can factor out an x squared. You're left with x squared minus 2. Actually, you can factor out x cubed. Yeah, that 0 at 0 has multiplicity 3. So your parentheses is just left with an x minus a 2. So you have a 0 at 0, and you have a 0 at 2. So let's go to our function. We can immediately plot a point right there at 0, 0, and at 2, 0. Right, this is going to be the graph of the original function f of x. Now let's use the first derivative to talk about increasing versus decreasing. The first derivative will be 4x cubed minus 6x squared. So it can change from, sorry, I shouldn't say it. The first derivative can change from negative to positive or positive to negative when the original function changes concavity. So let's see where this changes from positive to negative or negative to positive. Those happen at critical numbers. So I need to set my function equal to 0 and see where that happens. And then I need to ask myself, when does this function not exist? But this is a polynomial. You can plug anything you want into there. It's nice and smooth and continuous. So we're really only looking for these zeros. So you can factor out the x squared. You're left with a 4x minus 6. So 0 is a 0 of the derivative, and x is equal to 3/2, or 1.5, is the other 0. So let's see if we actually do change sign there. Actually, let's make one giant chart with the first and the second derivative all at once. So these are the places that I need to check for my derivative changing sign. Let's find the second derivative now. 12x squared minus 12x. If we set this equal to 0, we can pull out a 12x and we're left with x minus 1. So we have a 0 at 0 or a 0 at 1. These are the places where I might change concavity, right? Because when your second derivative changes sign, then your first derivative changes from increasing to decreasing, then your original function changes acceleration, changes concavity. So let's make one giant chart. Let's have these be the second derivative, these be the first derivative, and what is that going to imply about the original function? So we need to look at the first derivative when x is equal to 0. Right over here, we told ourselves that 0 was a 0 of the first derivative, so I might change sign there. And also at x is equal to 1.5. All right, our second derivative can change sign at 0. But I know it doesn't change sign at 1.5, right? That was not a critical value of my second derivative, but my second derivative might change when x is equal to 1. So it looks kind of gross. Let me clean that up. Okay. Now we need some test values. So let's look at -1, 0.5, 1.25, and something on the other side of that dashed line. Let's go with 2. So let's plug these test values into the derivatives that we're interested in. All right, when we plug -1 into the second derivative, we get 24. This is positive. My original function is concave up. I just don't know if it's concave up and decreasing or concave up increasing or concave up decreasing. And what tells me increasing versus decreasing? That's my first derivative. So if we plug -1 into the first derivative, we get -10. That's negative. So I'm concave up, but I'm decreasing. All right, if we plug 0.5 into the second derivative, we get a -3. So negative, negative. I know that I'm concave down. Now let's find the direction. If we plug 0.5 into the first derivative, we get -1. So it's negative. So I'm still decreasing, but now I'm concave down. It look like something like that. All right. Let's figure out what's going on with our second derivative at 1 point. Actually, you know what? Let's just use 2. Because if I use 2 and I figure out what's going on over here, then I also know what's going on over here. So if I plug 2 into my second derivative, I get a positive. What do I get? I get a positive 24. So I'm concave up. And then what is my first derivative on the right side of 1.5? So what's my first derivative at 2? That gives me an 8. So I'm increasing. So I'm increasing and concave up there. Oh, I seem to have skipped an interval. 1.25. What's going on at 1.25? I don't think we need another test interval. I think we can get around that. So my second derivative has to be positive there because it's positive over that entire interval. All right, and my first derivative has to be negative there because it's negative over that whole interval. So I have a positive second derivative. I'm concave up, but I'm decreasing. So I get something like that. So knowing that this is a polynomial, it's going to be nice, smooth, and continuous. The function is going to look something like this. Right here, we're concave down and decreasing. Here, we're still decreasing, but now we're concave up. Or sorry, we were concave up before, now we're concave down. And then what now? On the other side of 1, we continue to decrease, but now we're concave up. We're decreasing, but we're concave up. And then we're still concave up, but now we start to increase. Cool. So let's go over to our graph. We know it had that end behavior because of, we can take the limit as x goes to -infinity if we want to, but we know the shortcut by now. It's an even degree polynomial with a positive leading coefficient. So we knew we were decreasing, concave up, until we hit a 0. Right, 0 is where we changed inflection. And then we start to decrease there. So we're decreasing with negative concavity. And then at some point here, we change concavity. We go from concave down to concave up. And that concavity change happens right there at x is equal to 1. Oh, yes, that's right. Right, because here you change from negative concavity to positive concavity. So at x is equal to 1 right there, I change from concave down to concave up. But I continue to decrease until, where do I stop? 1.5. Right, so that value right there is 1.5. That looks right. And then I increase after that. I pass through my other 0 that I knew I was going to get at the very beginning. And I have that end behavior. Yeah, everything looks good.